Hi. Here we are to take two texts and we are to split the one on the right such that the first character of the second segment is the first character that is found in the left argument. Let me illustrate this. So let's say we've got this is the splitter characters, and this is the actual text that we want to split. So D doesn't exist on the left, Y exists on the doesn't exist on the left, A does exist on the left. So we want to split it here. We want to get dy and we want to get a log. And there are a few different ways that we can do this. Let's get started. So what we can do is we can find where we've got elements, their positions. So if we look up, so this is a lookup function, but this will look up elements of the right in the left, and we want the left in the right, so we can flip its arguments. So we can see that A is found position 3, P it says 7 because it doesn't actually exist there, so it goes to the next index over here, and L in position 4. We're not interested in all these positions, we just want the smallest one. So we can apply the minimum reduction on this. That gives us the 3. However, 3 is not actually the index we're interested in. We want to get one less than that because we want to split it, so we only get the first 2. So we can add -1 to this. Then we take this number and we use it to take this many elements from the right argument. And we can also use it to drop this many elements from the right argument. We want both to take and to drop, and we want them joined together. So the take and the drop, and we could concatenate them together, but that doesn't do anything because then we're just rebuilding the text from the right. No, we need to encapsulate them. So we need to pre-process the arguments to the concatenation function with an enclosure. And that gives us our result. There's one little issue here, and that is if the right argument, and which is the place where we look up elements from the left argument, doesn't have any dimensions, that is, if it's a scalar, then we get an error. And we can fix this by pre-processing the right argument with a comma, which is ravel. This makes it into a one element vector instead, and then it works. So we can give this a name. This is F. A different way to approach this begins off the same way. This time, let's stay explicit. So we've got dialog and APL. And we're going to do much the same thing as before. Let's look up the left argument in the right argument. We saw this before. Let's take the minimum. And now we want to partition the right argument. And the way we partition is using, or actually partition enclose is the more correct term, but using a Boolean mask that is as long as this or shorter. It could actually be one element longer, but that's not really relevant yet. We want a 1 every time we begin a new section and zeros for everything else. So this is a 3. That's where the second partition begins. We also want to begin at a section at position 1. Now we just need to create a Boolean mask that has these values. Now there is a function in APL that goes the other way. If you write 1 0 1 0 0, then we can use the where function to say where are the ones. But we want the opposite. We want to know, we want to start with 1 and 3 and do the inverse of where. Luckily, there is an operator in APL which is called the power operator, which can apply a function multiple times, including a negative number of times. So this creates the shortest possible Boolean result that satisfies that when you apply where to it, you get 1 and 3. So if we go in here and we use where inverse on this, that gives us the mask that we need. And then we take the right argument and do a partitioned enclose. Only the mask needs to go on the left, so we flip the arguments of this. And that gives us our split. There are still a couple of issues, as we have had before. If we have a scalar on the right, of course, then we get a rank error. But we can fix this by putting a revel over there. Another problem is what happens if the left argument contains the first letter. Interestingly, this actually works. But how is that even possible? For that, let's take apart our solution again. We generated these two, so we get a 1 because we want to start a position at the first position. And then we generate the lowest index where D appears, where a letter from the left appears, which is also 1. So what happens when there are duplicates for the where inverse? Then it says that there are 2 here. Maybe a little bit obscure what's happening, but let's say that we've got 1, 1, 3, 4, 4, 4, and 5. So these are the positions of our booleans. That means that we want to have 3 times a 1 at position 4. And that is exactly what the where inverse does. So similarly, we can go take this one and put where in front of it. So saying where are the ones? Well, there are 2 ones at position 2, and there are at position 1, and there are no ones at position 2. There's 1 1 at position 3. There are 3 ones at position 4. So the solution actually works, even though we are finding a match at the very first position. We can also take the solution and test it like the other one. So in this, then we would have the reversed index of. We put the left argument on the left and the right argument on the right. We can join the reduction to that. So we're doing the minimum of the flipped index of. Then we apply this. And then we have to apply this derived function to the result of the concatenation, which one way we can do this is like this. You can test that we're still explicit, but we've prepared all the pieces for a tacit conversion. You see that this works. And now we can get rid of all mentions of arguments. And this wants the identity function applied to the right argument. And we can call this G. Oh, we still need a comma over here. We need to pre-process the right argument using revel. So now we can write and it also works for scalars. Thank you for watching.